FMSec, which is a series of seminars and a network that tries to promote formal methods specifically in security. And today we have a talk by Bruno it's the intersection of both between security and formal methods. And I will say some words about Bruno. So probably all of you here know Bruno Blanchet. He needs very little introduction. He's a senior researcher at INRIA in Paris in the Prosecco team. And he's been a researcher with CNRS between 2001 and 2010, and between 2001 and 2010, also an independent research group leader at Max Planck. Many things can be said about him. All of you probably know of Bruno in the context of the tool called ProVerif and the tool called CryptoVerif, and not just those two tools, but a lot of things to do in formal methods and verification of security. And today we have the pleasure to hear a talk on ProVerif, and in fact, not on just any aspects of ProVerif, but the recent improvements that have been made in ProVerif by Bruno in collaboration with his co-authors Vincent and Véronique. And the floor is yours, Bruno. And if you do not object, as we told you, we are recording this talk.
Thanks very much for the introduction and for the invitation. And I'm happy that the talk is recorded. That's fine. Okay. So let me start. So I'm going to give you a little bit of overview of what ProVerif is, and then I'm going to focus more on recent improvement, as Johanna told, that are joint work with Vincent Cheval and Véronique Cortier. So first of all, our goal in this work is to verify security protocols. So security protocols are small programs that are designed to secure communication so they can satisfy various security goals. And they use cryptographic primitives like encryption, hash functions, and so on. So here I've shown a few examples that use security protocols like internet, Wi-Fi, mobile phones, and so on. So these protocols are really everywhere. In order to model such protocols, to verify them, we are going to consider an active adversary that can intercept all the messages that are sent on the network, that can compute his own messages, and that can send messages on the network as if they came from honest participants. And we are going to focus on the symbolic model. So in this model, the cryptographic primitives are considered as black boxes. So we do not study the algorithms that built these primitives. We just consider them as function symbols, like encryption is going to be a function symbol senc for shared key encryption. And then the messages are going to be terms on these primitives. So for example, here you have the shared key encryption of hello under the key K, which is senc of hello, K. And then the adversary is going to be restricted to compute only using these primitives. So this is the so-called perfect cryptography assumption. So you can decrypt only by applying the decryption with the correct key. And so the definitions of the primitives specify what the adversary can do. And then you can add equations between primitives to model equalities. For example, you can say that decryption of encryption yields the clear text. But the hypothesis that we use is that the only equalities that hold are those given explicitly by the equations that you write. So this model makes proofs relatively easy. So basically, you're going to compute all the knowledge of the adversary, which is still tricky because it's infinite in general, but it's much easier than reasoning about probability tincturing machines, bit strings, and so on. So ProVerif works in this symbolic model. So it's a fully automatic protocol verifier that can handle an unbounded number of sessions of the protocol on an unbounded message space. So this means that the problem is undecidable. It can handle a wide range of cryptographic primitives that are defined by rewrite rules or by equations. and it also handles various security properties, so secrecy, authentication, and some equivalences. I'm going to talk more about what these properties are a bit later in the talk. So in general, since the problem is undecidable, we cannot have a system that always solves the problem and always terminates. So in fact, ProVerif does not always terminate, and it's also not complete. So sometimes it is unable to decide whether the security property is true or false. But in practice, it's still efficient and precise. So let me show you a bit the structure of the tool ProVerif. So you can download this tool if you like at proverif.inria.fr. So this tool takes as input a description of the protocol that you want to verify in an extension of the Pi calculus with cryptographic primitives. And these primitives are defined by rewrite rules or by equations. And then it also takes as input the properties that you want to prove. So as I said, that can be secrecy, that can be authentication, equivalences. And then it's going to automatically translate the protocol and the primitives into a set of on clauses. And it's going to translate the properties that you want to prove into derivability queries on these clauses. And then it's going to use a resolution algorithm to determine whether the fact that you're looking at is derivable from the clauses or not. So when the fact is not derivable, then the property is proved. You are sure that the property is true. When the fact is derivable, the derivation is the witness of an attack, but it's the witness of an attack at the on-clause level. And in fact, there is an abstraction when you translate the protocol into on-clauses. So for this reason, two cases can happen. Either it's a real attack, and then the property is false, or it's a false attack. So in this case, it's an attack at the on-clause level, but not at the protocol level, at the Pi calculus level. And then you don't know. It's the case in which ProVerif is not complete. You don't know whether the property is true or not at the protocol level. So there is an attack reconstruction algorithm that is going to try to reconstruct a trace from the derivation. And if this attack reconstruction algorithm succeeds, then you are sure that the property is false. If the attack reconstruction fails, you don't know. So let me explain you a little bit the syntax of the input language of ProVerif. So obviously it's a bit simplified to give you an idea. So we represent messages by terms that can be variables like X, Y, Z that are going to be substituted by other terms. They can be names, A, B, C, which are going to represent constants, random keys, nonces, secrets, etc. And we have the constructor application f of m1 mn, which applies the function f to some terms m1 mn. And the function f, for example, can be encryption. And then you have processes that are going to manipulate these messages. So the output out of mn sends the message n on channel m, and then it's going to execute p. The input is going to receive a message on channel m, store it in variable x, and then run p. You have the nil process that does nothing. The parallel composition, p parallel q, allows you to run p and q in parallel, so you can have several participants that interact with each other, and you represent that with parallel composition. The replication, bank p, represents an unbounded number of copies of the process p in parallel. So that's the way to represent an unbounded number of sessions of your protocol. So you represent an unbounded number of copies of each participant of the protocol. The restriction UA generates a new fresh name A, and this is going to represent the generation of random numbers in particular. And then you run the process P using this name A. The destructor application is used to apply cryptographic primitives, but in this case, the cryptographic primitives can succeed or fail. So this is the case, for example, for decryption. So if you apply the function J to the terms M1, Mn. If it succeeds, you're going to store the result in the variable X and then run P. If it fails, you run the process Q. And you have the condition also, which is fairly standard. So if M is equal to N, then you run P, otherwise you run Q. So as I mentioned, you can have two kinds of cryptographic primitives, constructors and destructors. So the constructors built new terms. So they are free function symbols. So for example, shared key encryption is a constructor that takes two arguments, the ciphertext and the key, the clear text and the key, and returns the ciphertext. So in ProVerif, it's declared fun s-enc, so the shared key encryption function symbol, the type of the clear text, which is here bit string, the type of the key, which is key, and the type of the result, which is bit string. Destructors manipulate terms, so they compute on terms, and they are defined by rewrite rules. So for example, decryption, you can define it by this rewrite rule that says that if you decrypt with SDEC a ciphertext s-enc of mk using the correct key k, then you obtain the clear text M. So here you can declare it in ProVerif by first declaring its type. So SDEC takes an argument of type bstring and a key and returns a bstring. And you give the rewrite rules with this reduc keyword that says that SDEC of s-enc of mk, comma k is equal to M. So using such constructors and destructors, you can represent many primitives, public key encryption, signatures, hash functions, and so on. For some primitives, you need to use equations and not rewrite rules, but I'm not going to go into that in this talk. So just to illustrate with a small example, I'm going to consider a simplified version of the Denning-Sacco public key distribution protocol. So in this protocol, the participant A generates a fresh shared key K, and the goal of A is to send this key to B so that the key K is shared between A and B. So A is going to sign this key using a secret key SKA and encrypt it using the public key PKB. And then B is going to reply with the encryption of some secret S under the shared key K. So the idea is that when B receives the first message, B is going to decrypt because it's encrypted under the public key of B, so B can decrypt. B is going to verify the signature. And since it's signed with A, B is going to be convinced that the message comes from A. Actually, there is an attack against that, but let's consider that as the goal of the protocol. And then B obtains the key K, and B can reply with the encryption of some secret with K. And normally, this secret S should remain shared between A and B and not known by anybody else. So if we model that in the ProVerif, we first need to generate keys. So we generate a signature secret key SKA, then an encryption secret key SKB. So SKA is for signature and SKB is for encryption. That's why the type is different. Then we compute the public key PKA corresponding to SKA, the public key PKB corresponding to PKB, and we output PKA and PKB on a public channel C. So it is obviously very important to give the public keys to the adversary, otherwise the adversary would be very weak. Then we are going to model in parallel A and B, and A is going to be replicated. So we run an unbounded number of executions of this protocol. And there is a small trick at the beginning of the code for A. We input a public key xpkb, which is going to be the public key of the interlocutor of A. So in the two messages that are at the top of the screen, I assume that A talks to B, but in fact, A can talk to anybody. So I model that by receiving the public key of the interlocutor here in the variable xpkb. Then I generate the fresh key K. I output the first message, which is the encryption, the public key encryption of the signature of K under SKA, unencrypted under xpkb. And then I'm going to receive the second message, decrypt it with K on terminate, I do nothing. And for B, again, it's replicated as for A. We receive the first message, we decrypt it using SKB. We verify the signature using PKA. And that gives us the secret key K, and we output on the public channel C the encryption of S under K, which is the second message of the protocol. So this is a simple model of this protocol in ProVerif. So that was the input language. As I said, this language is translated into on clauses. So the first encoding of protocols into on clauses was given by Weidenbach in 1999. In the encoding that we use in ProVerif, the main predicate is ATT, attacker. So attacker of M means that the attacker may know the term M. And using this predicate, we can model both actions of the attacker and of the protocol participants. So as I said, processes are automatically translated into on clauses that use this predicate. So this is joint work with Martin Abadi. So to code primitives, we first consider the encoding of constructors. So if we have a constructor F of arity N, then if we are going to have the clause attacker of X1 and etc. on attacker of Xn implies attacker of F of X1 Xn. So this is because if the attacker has X1 Xn, it can apply the function F and obtain F of X1 Xn. So for example, for shared key encryption, if the attacker has the clear text M and the key K, then the attacker can compute the encryption of M under K, which is S_unc of MK. For destructors, so if we have a destructor G defined by a rewrite rule G of M1, Mn implies M, we are going to have a clause attacker of M1 and etc. on attacker of Mn implies attacker of M. So this is because if the attacker has instances of M1, Mn, it can apply the function J and obtain the corresponding instance of M. So for example, for shared key decryption, we have these rewrite rules as dec of S_unc of MK, K gives M. So we are going to have the clause if the attacker has S_unc of MK, so this is the ciphertext, and the attacker also has the key K, then the attacker has the clear text M. So that models the capabilities of the adversary to compute messages. And then we want to model protocols. So the main idea is that if some principal A receives messages M1, Mn, and sends as reply the message M, we are going to have the clause attacker of M1 and etc. on attacker of Mn implies attacker of M. So for example, in the Denning-Sacco protocol, upon receipt of the first message, the encryption of the signature of Y under SKA encrypted under PKB, B is going to reply with the encryption of S under Y. So we are going to have this clause. If the attacker has the encryption of the signature of Y under SKA encrypted under PKB, then the attacker can send that to B. B is going to reply with the encryption of S_unc of S under Y. So the attacker gets this message by intercepting the message sent by B. And so the attacker has S_unc of SY. So this is what this clause says. And using these clauses, we can prove secrecy. So there is a theorem saying that if the fact attacker of M cannot be derived from the clauses, then the term M is secret. So intuitively, the term M cannot be built by an attacker. And the resolution algorithm will determine whether a fact is derivable from the clauses or not. So in ProVerif, if you want to prove the secrecy of S, you are going to use this query attacker of S, and then ProVerif is going to test whether the attacker can compute S or not. And then we use a resolution algorithm and the clauses. So the resolution is a resolution with free selection. So I'm going to explain you a little bit what it does. So resolution combines two on clauses together. So if you have one clause, which is H implies F, and another clause, which is F'1 on H primes implies F prime, and sigma is the most general unifier of F on F'1. So this means that sigma F is equal to sigma F'1. Then we have this clause, H sigma on H prime sigma implies F prime sigma. So to give you an intuition, we use the first clause to conclude F sigma from H sigma. But F sigma is equal to F'1 sigma. So we have already proved F'1 sigma. Then if we also have H prime sigma, then we can conclude F prime sigma by the second clause. So this is the resolution. And then with resolution with free selection, this rule is applied only when the literals F and F'1 are selected. There is a selection function that selects one literal in each clause, and that restricts resolution in this way. So this selection function basically is going to select some hypothesis, not of the form attacker of X, when there is such a hypothesis. Otherwise, it's going to select the conclusion. So the key idea of this choice of selection function is to avoid resolving on facts of the form attacker of X, because such a fact can unify with any other fact attacker of M, and so it would cause many resolution steps, and it would immediately lead to non-termination. So the algorithm performs these resolution steps until a fixed point is reached, that is, only no new clause can be produced. And it keeps only the clauses whose conclusion is selected. So because we keep only those clauses, the obtained clauses are much simpler, and then it's much easier on the final set of clauses to determine whether some fact is derivable or not. And then there is a theorem expressing the soundness and completeness of this resolution with free selection. So it says that the obtained clauses derive exactly the same facts as the clauses that we had initially. So until now, I talked about secrecy, but there are other properties. So one interesting kind of property is correspondence assertions that model authentication. So the goal of authentication is to express that if some participant thinks he talks to, so if some participant A thinks he talks to B, then A really talks to B, and in particular, B thinks he talks to A. So we are going to express that using correspondences between events. So in the example of the Denning-Sacco protocol that I displayed again, I can add here an event EA saying that A started the protocol with his own public key, PKA. The public key of the interlocutor is XPKB, and the shared key that is exchanged by A is the key K. And then here I have an event EB that says that B finished the protocol, thinking he talks to the participant with public key PKA. His own public key is PKB, and the shared key is K. And what we are going to show is that if event EB is executed with some arguments X, Y, Z, then event EA is also executed with the same arguments X, Y, Z. So that shows, well, if it's true, because in fact it's not true for this protocol, but if it's true, it would show that EB if EB terminates the protocol thinking it talks to A, then A started the protocol thinking it talks to B, because the public key PKB would be the same on both sides. And the shared key exchanged by A and B would also be the same on both sides. So that's an authentication property. And the final class of properties that ProVerif can prove is equivalences. So in general, process equivalences express that an adversary cannot distinguish between two processes, two protocols. So that's a very powerful way of specifying properties, in particular, because in principle, you can say that the protocol is indistinguishable from some ideal protocol that serves as a specification. But in general, process equivalences are very difficult to prove. So ProVerif only restricts to a small class of equivalences. So there is the notion of strong secrecy that says that the attacker, the adversary, cannot distinguish when the value of a secret changes. So it's a stronger notion of secrecy than the one that I mentioned before. That's why I name it strong secrecy. And then there is the notion of diff equivalence, which expresses equivalences between processes that differ only by the terms that they contain. So the idea is that the processes must have the same structure, same replication, same inputs, same outputs, but possibly with different messages. And then we can, ProVerif can try to prove that these two protocols are indistinguishable from the point of view of an adversary. And that can be used to model, for example, the protocols that rely on weak secrets and passwords. So to show that you cannot do guessing attacks on passwords, you can use this notion of diff equivalence in a particular case. So that was basically the overview of the tool. I don't know if you already have questions at this point. If you want to ask questions, perhaps you can, but otherwise we can take all the questions at the end of the talk. Okay, let me continue, and you can ask questions at the end probably. So recently with Vincent, Cheval, and Véronique Cortier, we did a lot of extensions of this tool. And in particular, we added support for natural numbers, for temporal correspondence queries, precise actions, axioms, restrictions, lemmas, proofs by induction. So I'm going to explain you a little bit what we did for all these extensions. So first, natural numbers. So we consider a new type NAT with specific operations, addition and subtraction between a variable and a constant natural number. So we can model counters basically using these operations. And we allow comparisons between variables containing natural numbers or constants. And we allow a predicate testing if a term is a natural number or not. So here I showed a small example of protocol that receives two values, min and max, so two natural numbers. And it's going to output all the natural numbers, all the encryptions, sorry, of the natural numbers between min and max. So the details are perhaps not really important, but I just wanted to illustrate that you can compare natural numbers, you can do addition, you can receive natural numbers and send them on the network console. So this is implemented by extending a little bit the on clauses, adding constraints is nat of m to say that m is a natural number, not is nat of m to say that it's not a natural number. So for the else condition of the predicate is nat, and comparisons m greater than n plus n. So the big M and big N are terms, and the small n is a constant natural number. And these constraints are simplified using the Bell-Medford algorithm to determine whether they are satisfiable or not. Then temporal correspondence queries. So these are an extension of the correspondence queries that I mentioned. in which we use a special type time for temporal variables. And we can associate a fact F with a temporal variable I. And in particular, event EV at n means that the event EV is executed at the nth step of the trace. And then we can compare temporal variables. So for example, here we have a correspondence that says that if the event A of X is executed at step I, and the event B of X is executed at step J, then I is strictly smaller than J. So this means that the event A of X has happened before the event B of X. So we allow comparisons. We do not allow additions of constants and things like that. So the steps are not really numbered. We just say that something happens before something else or strictly before. And this is encoded into uncloses using special natural number constants, I less than J, and I less or equal to J. Now, precise actions. So this is an interesting extension because it allows to improve the precision of the tool ProVerif and to solve some false attacks. So to illustrate that, I consider a simple toy example. So in this example, I have a participant A that sends 3 messages, the encryption of some secret S under the pair K1, K2, the encryption of K1 under K, and the encryption of K2 under K. And then I have a participant B that acts as an oracle for decryption under the key K. So it receives a ciphertext, the encryption of Y under K, and is going to reply with the clear text Y. But it's going to do that only once. So that's very important that B does that only once. So this means that the adversary can use B to decrypt either the encryption of K1 under K or the encryption of K2 under K, but it cannot decrypt both. And since it cannot decrypt both, it will not be able to obtain both K1 and K2. And so it will not be able to decrypt the encryption of S under the pair K1, K2. And as a result, it cannot obtain S. So that's what we want to show. So if we translate that as a process, we are going to have this process on the left here, which shows that A outputs the 3 messages, and B receives a message on channel C, stores it in X, and replies with a decryption of X under K. And we run A and B in parallel, and A and B are run only once. They are not replicated. So if we translate that into uncloses, we are going to get the clauses on the right. So for A, we have the clause attacker of S_unc of S, K1, K2 for the first message, attacker of S_unc, the K1 under K for the second one, and attacker of S_unc of K2 under K for the third one. For B, we have the clause attacker of S_unc of YK implies attacker of Y. So B can decrypt the ciphertext under K. And we have additional clauses for the attacker. So the attacker can encrypt. If it has X and Y, it obtains the encryption of X under Y. It can decrypt. If it has the encryption of X under Y and the key Y, it can obtain the clear text X. And it can also construct pairs. There are other clauses, but that's enough for what I want to say. And then the secrecy of S will be proved when attacker of S is not derivable from these clauses. But the problem is that on clauses can be applied an arbitrary number of times in derivations. So here, the clause for B can be applied not only once, but any number of times you like. And for this reason, at the on-clause level, the adversary will be able to decrypt several messages using B, using this clause. And then the proof of the secrecy of S fails because using the clause for the first message, you obtain attacker of S_unc K1K. And then you can decrypt that using the clause for B. So you obtain attacker of K1. You can do the same for attacker of S1 K2K. You decrypt it, you obtain attacker of K2. You use the clause for pairs to obtain attacker of K1, K2. Then you use the clause for the first message S1 of S and the K1, K2 to obtain that here. And then you decrypt S1 of S K1, K2 using the key K1, K2, and the attacker obtains S. So here we have a false attack. That's exactly that. It's a derivation, but this derivation does not match an execution of the process, because in this derivation you run B twice essentially, and that's not allowed at the process level. So what can we do to solve this problem? We can annotate with the precise keyword the input of B, and then this tells ProVerif to analyze more precisely this input. We will see later how this is implemented. If we want to analyze all inputs and outputs precisely, we can use this global setting set precise actions equals true. However, it's going to slow down the tool in general. So you should use precise only when you really need it, because otherwise it can slow down or even lead to non-termination. So in fact, we implement precise using axioms. So I'm first going to explain what axioms and restrictions lemmas are, and then explain how we implement precise. So restrictions are queries, like correspondence queries, for example, that are used to restrict the traces that are considered in the other axioms, lemmas, and queries. So you are going to give some correspondence, and you are going to restrict yourself to the traces that satisfy this correspondence. And then when you query attacker of S, this query holds if no trace that satisfies the restrictions R1, Rn reveals the secret S. And to do the proof, ProVerif is going to assume that the axioms A1, Am hold. So the axioms are properties that hold on all traces that satisfy the restrictions, but they are not proved by ProVerif. So they are assumed. They can be proved manually, for example, if that's a property that ProVerif cannot prove. They could be proved in some other tool, perhaps. I don't know. So you are free to prove axioms the way you like. And then you can also give lemmas, and ProVerif is going to try to prove the lemmas L1, Lk in that order, using all axioms and all previously proved lemmas to help do the proof. And finally, ProVerif is going to try to prove the query attacker of S, using all axioms and all lemmas. So now, how do we implement precise actions, and how do we use axioms, restrictions, and lemmas in the internally in the tool? So in fact, the option precise is encoded as an axiom. So in the example that I consider, I'm going to consider an event precise that takes two arguments, an occurrence name and some bit string. And in the process B, after the input that is tagged precise, I'm going to add a new awk of type occurrence that creates a fresh name awk of type occurrence. So there is a distinct name awk at each execution of the input. Then I execute the event precise awk X, saying that I have executed the process B with the message X on the occurrence awk. And I continue the rest of the process normally. So here I would put the decryption of X and the K. And then I have this axiom saying that if I execute event precise with awk on some message X1, and also precise with awk on some message X2, so it's the same awk but potentially two different messages, x1 and x2, then in fact, x1 must be equal to x2. So this is because since I have a distinct name hoc for each execution of B, having the same hoc means that I'm in the same execution of B. So then the message that is received by the input must be unique. And for this reason, I'm sure that x1 is equal to x2. Now, using such axiom or lemma, I can modify the clauses that are generated during a resolution. So suppose that I have a lemma of the form, if I have a conjunction of facts fi, then I have a formula phi. And I generate a clause H implies C during resolution. If for all I, fi sigma is in H or is equal to C. So this means that all hypotheses of the lemma are proved in the instance given by the substitution sigma. In that case, by the lemma, I can conclude that phi sigma is also true. And then I'm going to add this property phi sigma in the assumptions, in the hypothesis of the clause. So I transform the clause H implies C into H and phi sigma implies C. So in the example of precise, I have this axiom precise of hoc x1 and precise of hoc x2 implies x1 equal to x2. And during resolution, I'm going to generate the clause event precise hoc of S onc K1K and event precise hoc of S onc K2K implies attacker of S. So this clause means that if I used B to decrypt S onc of K1K, and I also used B to decrypt S onc of K2K, then I'm able to obtain S. By the lemma, we can transform this clause into this one. So here you can see that the event precise are an instance of the hypothesis of the axiom. So I can conclude the conclusion of the axiom x1 equal x2, which is here S onc of K1K equals S onc of K2K. So then I'm going to add this equality in the hypothesis of the clause. But this equality, in fact, is false because K1 is different from K2. So S onc of K1K is different from S onc of K2K. And then for this reason, the clause is removed, and that removes the false attack that we had before. Then we can generalize this to proofs by induction. So if we want to prove a query, we can use that query itself as a lemma on a strict prefix of the trace. And thus we do an induction on the length of the trace. So intuitively, if we have a clause H implies C, H happens strictly before C. So this is intuitive. In fact, this is true for events. For other facts, it's slightly more complicated to formalize, but that's the intuition. And then we consider some inductive lemma, the conjunction of Fi implies phi. So in this case, we know that the formula phi holds before or at the same time as the latest hypothesis Fi. And so if we have Fi sigma that is in H, then we know that Fi sigma is true strictly before the conclusion C. And so the conclusion of the lemma also holds strictly before the conclusion C. And we can add phi sigma in the hypothesis of the clause as before. So the only difference with the previous rule is that we do not allow Fi sigma to be equal to the conclusion C, because in that case, we do not have the strict ordering that we need to do the induction. That technique also works for a group of queries, and then we can perform proofs by mutual induction using this idea. Yeah, I think I was told I need to talk for about 45 minutes. Should I stop or conclude quickly, or should I continue a little bit?
I would say that we can continue for another 5 minutes or so,
Okay.
and then we'll take some questions.
Let me try to conclude in 5 minutes.
Okay, it's not a disaster, so we'll try 5 minutes and then we'll see where we are.
So let me give you a short example of proof by induction. So you have here a process that increments a cell, and we want to prove that this cell is always a natural number. So we have these clauses for the cell. Initially, the message 0 is sent on the channel cell that represents the memory cell. So we have mess of cell 0, and we also have the incrementation done in the process queue. So we have mess of cell I implies mess of cell I plus 1. So we cannot, need to stop, we need to stop resolving on this cell on mess of cell I, because otherwise we would have a loop in which we could resolve the first clause with the second one, obtaining mess of cell 1 and then mess of cell 2 by resolving again, and so on. Furthermore, the attacker is untyped. So in fact, I may a priori not always be a natural number. And so in the first step, we cannot prove that this cell always contains a natural number. But we can do it using inductive proof. So we do here in an induction now, and we can use as lemma the property that we want to prove, that is if we have X in the cell, then X is a natural number. That transforms the second clause into this one, adding is nat of I. And we also use this setting, so it's a bit technical, but we need to resolve at least once on a predicate mess of cell X. And this, we use this setting no unif in a few times to do that. And then the proof succeeds because basically we obtain two ways of having mess cell X, which is either a mess cell 0, and 0 is a natural number, so that's fine, or is the clause mess cell I and is nat of I implies mess cell I plus 1. And I plus 1 is a natural number when I is a natural number, so it is a natural number in this case. And we have proved that the content of the cell is a natural number in all cases. So using all these extensions, we managed to improve the expressivity of the tool ProVerif. And so here I have a table of a bunch of published and unpublished protocols that initially were not proved, or ProVerif did not manage to find an attack, so it did not manage to decide whether the properties were true or not. And thanks to our extensions, we now manage to either prove the property when it's a green mark, or we manage to find an attack when it's a blue thunder. And you can see what extensions we used in each case. And we also improved considerably the speed of the tool by rewriting and optimizing many of the algorithms. So I don't think I'm going to go into the details of that in the interest of time, but I can tell you that for subsumption, we used the idea of feature vertex indexing by Schulz, and it was really important to speed up the tool. I'm not going to detail the other improvements, but I can just show you the graph. So in linear scale, for a group of 42 files that models protocols of the noise framework, before our improvements, it took more than a week to verify them. And after our improvements, the runtime reduced to 20 minutes. So it's really a huge speed up. And in log scale, you can see what it does for other examples. So here you see the second example here is noise again. So from 1 week to 20 minutes. But for TLS, we go from 8 hours to 32 minutes. For some avionic protocols, for 11 hours to 17 minutes. For a voting protocol, from 3 days to 5 minutes. So huge speedups. And we also improved the memory consumption quite a bit by improving sharing. So what we want to do next, well, there are many things that can be done. Vincent has a lot of ideas of extensions of ProVerif. So integrate GSVerif, which is a tool that generates axioms automatically by looking at the form of the protocol that you want to verify. You might want to handle more equational theories, in particular the theory for XOR, for groups. We might want to go beyond the notion of diff equivalence, proving trace equivalences, for example, and possibly other extensions that could be suggested by users. So if you want more information on the extensions, you can see our paper that is going to appear at Security and Privacy next week. Thank you very much.
All right. Thank you, Bruno, for speaking. It's a very interesting conversation. I'll start with a question myself, and then I'll open the floor to everyone else who might have questions. So the first aspect about adding integers, I wonder if you looked, or if you're looking at the fact that once adding integers, support for integers into ProVerif, you can do an emulation of some computational aspects. And if you looked at anything like that, I know, of course, of CryptoVerif and so on, but using integers to do a very crude computational reasoning.
So we did not look at that. Basically, we think that our model of integers is limited to counters. Mm-hmm. So it would be rather weak to do some computational verification. It's good to model protocols that use counters to, I mean, if you increment a nonce every time you encrypt, for example, that can be modeled. If you allow some interval of counters when you receive a message, for example, to kind of timestamps, perhaps that would be an integer that is allowed in a certain interval, then you can also try to use integers to model that. But for computational verification, I think it's too weak.
And almost the same question applies for precise actions that are precise in order to model distinguishers, but not probably, again, not really, only to select an action versus another actions. Is that true?
So I'm not sure I understood the question. So
to use precise as in the axiom that behind the axiom, the keyword would be precise in order to model distinguishers. So to take this particular, to make sure that this particular action is being performed versus another action, and model again distinguishers in the sense of computational verification.
Not in the computational sense, but if I remember correctly, I think it helps for some equivalence proofs. So if sometimes you can have false attacks because the tool thinks that it can do different things on both sides. And with precise, it can sometimes be able to show that the equivalence becomes true. So I gave an example that is for reachability property, but this idea also applies to equivalences.
Makes sense. Okay, I already asked 2 questions, so I'll see if some of the other attendees have questions.
Hello, am I audible?
Yes.
Yeah, okay. Hi, Bruno. Thanks for the very nice talk, actually, and a very nice overview of ProVerif. So I was wondering, so you mentioned that there is, because of the abstraction gap between the Horn clauses and the pi calculus specification, ProVerif sometimes gives some false positives, right?
Yeah.
So you gave a nice example of a false positive which arises in the secrecy case. It's basically because of the lack of resource interpretation at the Horn clause level. You can use the same clause multiple times, right?
Yeah.
So I was wondering, maybe you can, if it is possible, if you can give an example of if, these kind of false positives for other properties, maybe for equivalence. So basically, ProVerif
so
detects yeah.
For equivalences, you can have many more false positives because the equivalence notion is really strong. So the ProVerif can show an equivalence only if during the whole execution, you can maintain the property that the processes only differ by the terms that they contain, by the messages. And so as soon as you take a different branch, the equivalence is broken. It cannot be shown by ProVerif.
I see. So how does ProVerif, what is the underlying algorithm ProVerif uses for proving equivalences?
So it's also a translation into on clauses. So basically the idea is to model the two processes that you want to prove equivalent as a single called by process. So it's a process in which the messages are not single terms, but pairs corresponding to the left and right side of your equivalence. And then proving a reachability property on these by processes, basically.
Ah, I see. So this is like self-composition, right? Yeah, okay.
Yeah, it's a composition of the two protocols that you want to prove equivalent. I think you could say that.
Yeah, right. I see. Okay, thank you.
Bruno, you also have two questions in the chat. Can you see the chat, or do you want me to read them?
I do see it. So the first question is Precise integrated into the latest online version of ProVerif? Yes, it is. So you can use it and run it right now. Can Precise be used to stop false attacks against commitment protocols? I would say yes. So, well, I'm not entirely sure because, well, I would see to test to be completely sure, but I think yes. So basically, Precise can eliminate all false attacks that happen when you reveal a secret at some point, but the protocol needs that to be secret before to be secure. So I think that's exactly what you have in commitment protocols. So yes, I think yes.
Okay. I will ask one other question before someone else may have one. So this, you mentioned here that Vincent would like to integrate GSVerif with ProVerif. Is GSVerif something that is available?
Yes, it is available. It's probably more in a prototype status than ProVerif, but yes, it is available.
Okay, all right. I suppose on your, if I just Google on the INRIA
so
website,
it's on
I'll find it.
Vincent's webpage.
Okay. All right. Any more questions?
So I did not insist too much on that, but Vincent did a lot of implementation work. So all these extensions are in fact mainly Vincent's work.
All right. Well, we thank you for the talk. I think there are no more questions. And in the end, we did stick to time quite well. We started a tiny bit late. Yeah, apologize from the beginning for those who started at the beginning. And thank you once again, Bruno.
So thank you, everybody. Thanks again for the invitation.
Thank you. The talk will be available online and you can watch it later online as well for those who want to recap again. And I'm sure that Bruno will be happy to answer questions offline as well.
Okay, sure, yeah. Feel free to contact me.
Thank you, everyone.